Okay, so the first thing I want to talk about, which I find to be really, really important, is being able to organize all of your files in different folders. That way, we're trying to look for a file that might be working on is not going to get lost in the hundreds of other files that you have for robotics. So, how I organize my files, I have two flash drives. One flash drive is this personal file, which has the 2020 robot CAD on it, and the other flash drive is this one, which is a little bit smaller and just has a lot of the hardware and other components that you're going to be needing to use to build the robot in CAD, obviously. So for my personal flash drive, I have my 2020 robot folder open. And the first thing I have here is the CAD of the field. And I like to use that just to kind of get an idea when the kickoff first happens. I usually download this file. Usually comes out the Saturday or Sunday of kickoff, and it gets a really good idea of kind of how big the game pieces are, um, with respect to the entire fields and what things are going to kind of look like. Um, and I reference that a lot when I'm doing like trying to get autonomous distances, and heights and angles and all that kind of stuff. And then you can see my next 7 or 8 folders are all the subsystems that I have. So there's the climber subsystem, fortune wheel, frame brackets, intake, prototype, shooter, tower, and tube. And so whenever I'm creating a part or a file for that subsystem, whether it be, for example, intake, I always put that file in the intake folder. So like I have the intake polycord, or the intake motor, all that kind of stuff. And it's also important to note these three folders up here because you go right from, once you are from CAD to manufacturing. I like to put all the parts I'm going to be manufacturing out of materials, so 3D printed parts. Whenever I'm creating a file that I'm going to be 3D printing, I put that in the 3D printed folder. Same with aluminum, so this is all the sheet metal stuff I end up seeing, and same with polycarb. That way, when it's time to machine the parts, when the CAD's approved by the mentors or captains or whatever it is, I can just go right into one of these folders, choose the file, and bring it into CAM, which we'll talk about later, to be manufactured. And that way I'm not sifting through all these files looking which one do I need to manufacture, which one do I need to, so I just put it in a folder that you're going to be manufacturing parts with, and it saves a lot of time in the long run. Um, and so, yeah, that's kind of the overview of this flash drive with all subsystems. I do have some junk down here. It kind of just, you end up, junk ends up happening to be placed at the bottom of these flash drives, and they kind of sit there, and I'm lazy, and it's whatever. And then the other flash drive I have is all the CAD that I've gotten from the first suppliers. So a lot of that is like mechanism wheels, which I don't CAD myself. I get from the suppliers like AndyMark, treads, gearboxes, gears, Falcon motors, electronic stuff. So like Victor motor controllers, RoboVios, radio, everything is here. And it's important to know that all of that stuff can be found on the supplier's websites. So, like for example, AndyMark is a big supplier, and if you're trying to find a gear, because right, catting a gear, you can do it, and I'll tell you guys how to do it. But it's way, way, way simpler just to go Google AndyMark, and they have all the CAD files right here. You just click on it and download it, and it goes, and I put it right into that smaller hardware flash drive. And that's really helpful because that saves a lot of time, and that way I can reference dimensions. Once I download this part, I can reference the dimensions, whether it be pitch diameter, hex bore, size, all that kind of stuff is right in the CAD file. It makes it extremely easy to kind of go from there to design more complex parts with these smaller parts in it. So that's good to know. AndyMark is a huge one. Vex Robotics, if you search up Vex Pro Robotics, they have a lot of parts too. Um, so for example, I usually go into here, and then it would be under hardware, and there's all sorts of stuff. So like if you're looking for a bearing, there's bearings, and again, if you scroll down to the bottom of their page, every single Vex product has a CAD file for it, which is unbelievably amazing. And so you just go here, click CAD files, look for what you need. There's a bunch of different bearings, and hit download and put it right into that 4 gigabyte file the small one that I showed you. So Vex, AndyMark, big ones. Also BaneBots has similar things, but the majority of the parts come from Vex Pro and AndyMark. All right, so the next thing I want to talk about is kind of how you start a file and how you set up that file so that it fits with the format that we use or that I like to use. So the first thing you want to do, click on your SolidWorks 2020, whatever year it is, app over here. This window will pop up. It loads pretty quick. And then you can also create a new part, new assembly, or new drawing. So for this example, I'm going to be doing a new part. Double click on that. And the first thing you're going to do once this window opens, first thing I always do is hit the little settings icon right here, which is options. Go to document properties, units, and then make sure that your units are this IPS units, which is inches, pounds, seconds. It's the SAE units, the American units, which is what almost all of the parts that we use for First Robotics are in. They're in inch, pound, second units. I have 2 decimal places for accuracy. Sometimes you can go 3 or 4. It doesn't really matter. It's just kind of whatever you prefer. And then hit OK. And that'll save those settings. Now, kind of an overview of what you're seeing on the screen here. These are kind of like the menus. So you have the sketch menu, has all the sketch commands. Features have a little bit more complicated, I like to say, like the 3D demands, so making a 2D sketch into a 3D object. And then as you get more complicated, there's also simulations. So you can do like stress tests, which I'll show you guys how to do in future videos. But that's, a lot further down the road. You need a part in order to do simulations, obviously. So also on the left here, you'll see this box. This is what they call the tree. And this is where kind of all the important steps of making a part start. The idea tree is what they call it. And so you have your 3 types of planes: front plane, top plane, and right plane, as well as your origin is defined. You can see history of what you've done. So like you've created a line here, you've extruded it here, all that kind of stuff. Not as important, obviously. And then we also use sometimes appearance. So if you want to make the object that you're working on like pink, red, black, whatever color you want, you can do right click and add appearance, which I'll talk about in future videos as well. But that's all kind of there for you to kind of create the part. Hold on, I lost my, there we go. And so yeah, that's kind of how things are set up. Now, to start to create a sketch, the first thing you need, or to create an object rather, the first thing you need is a 2D sketch. So you create a 2D sketch, and then you extrude that sketch, which I'll show you how to do, into a 3D object. So to start with a 2D sketch is hit this sketch button right here in the top left corner. It doesn't particularly matter which plane you select. However, you do want to keep them consistent. So that's used when you're making assemblies, which is assemblies are a bunch of parts combined. If they're in different planes, you're going to do more work for yourself later on, trying to rotate those parts to kind of align how you want them to be. So I always just choose top plane. It's kind of a standard, industry standard. But again, it doesn't. If you make a mistake, it's not a huge deal. It doesn't really matter. You'll just have to do more work in the future, but it's not a big deal. So right now, we're looking dead on at the top plane. You can tell if you hit space bar, you can kind of see we got a dead straight on view. If not, you can. So this is like rotating your view essentially by holding down the scroll wheel of your mouse. You can kind of pan around, and then choose top plane again. So first thing you're gonna do to create a 2D sketch. Sketches are made of lines, circles, arcs, all that kind of stuff. Just for this introductory video, we're going to be making a simple shape. We're going to go with a trussed triangle, which is something they use a lot in First Robotics when you're manufacturing parts. It's what I used for the majority of my parts. So you start with a line. That is the L command on your keyboard. You click on the point, and now you're able to drag this line all around wherever you want it to go. Once you have it, roughly, so you can see the dimension is right next to the little pencil icon, 3.8 inches, 4 inches. So you want to make like a 5 by 2 triangle. I'm going to go, it doesn't matter, just go roughly to 5. It doesn't matter how close you are. Then you're going to go up, so like roughly 2 inches, and then back down across. And now we have a triangle, right? Now, SolidWorks is what they call a dimension-driven software, which means everything that you ever make needs to be dimensioned. And if you over-dimension things, which I'll talk about, you can run into some issues, but I'll tell you guys how to avoid doing that. So right now we have a triangle. It's roughly 5 by 2, but not exact. So now I'm going to hit the D key, which is, again, you can also hit Smart Dimension, which is up here in the corner. And you can see it has like a little dimensioning symbol next to your cursor. So you click the line, just tap it once, pull down, and click again, and a box automatically pops up, which has the current dimension, which is 4.73 yada 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 inches. We're going to hit 5, enter, and now this line is 5 inches long. Now, we've essentially established a line of reference. So every other line that we're going to dimension is going to be to scale or in reference with this 5-inch line. So if we dimension this line now, if we make it 5 inches, it should be the same length as our bottom line, right? We only want it to be 2 inches, so I'm going to make it 2 again, click on the dimension, hit 2, and you're all set. Now, what I mean by over-dimensioning is the software is smart enough to know kind of trigonometric functions of how a triangle works. So it knows this angle right here is a certain angle based on just these two side lengths. So if you try to go in and dimension this angle, dimensioning angles, you simply hit one of the lines and the other one and dimension. Now a box pops up. It turns either yellow or orange. Yellow or orange is bad news. That means stop what you're doing, don't hit enter. What you want to do, because it already knows this angle is 21.8 degrees, just hit X. That means you don't want to dimension that thing, it's already dimensioned for you. So now we have, I can rotate around our triangle dimensioned correctly. Again, so if you like look around and now we're at like this weird angle, what you can do is simply hit spacebar and then go so that we're flat on, again, hit the plane that is kind of in line with what you're drawing on the sketch. Okay, so once you have this triangle drawn, the next step is to do what they call an extrude. And what an extrude is you're essentially pulling this 2D sketch into a 3D object. And an important thing to note with features like extrude, so you can access the extrude feature under the features menu and then hit extrude, which is kind of 2 clicks and more work than it has to be. What I've gone ahead and done over the years, I've kind of learned to create what they call keyboard shortcuts. So you press a key and it goes right to that command. So, or that feature rather. So right now I have it set to E, so whenever I hit the E button, it goes right into the boss extrude. And so in order to create keyboard shortcuts, which I recommend you do for all the basic tasks like drawing lines, circles, extruding, all that kind of stuff, you hit Tools, go down to Customize, Keyboard, and then you can search the thing you're trying to make a keyboard shortcut for. So extrude, for example, pops right up. Extrude, I have set to E. You can change it to R. I've already have a thing for R, so it's not going to work. But you can make it whatever keyboard or key you want it to be. So E works for me very well, so keep it at E. So once I hit E, again, you can see this kind of boss extrude, aka the extrude feature window pops up. And that lets me know that currently I am in the extrude feature. If it doesn't pop up, you're not going to be extruding the 2D sketch. It's just not going to work. And that's really helpful, so you know kind of in the idea tree, which again is this part on the left, the idea tree, you're knowing what command you're currently working on. So I'm obviously again doing the extrude command, as you can see up here, boss extrude. And this number right here is the main one that you're going to be working with for now, which is how much of the 2D sketch is going to extrude. So you can extrude it an inch, maybe, so 1 inch. And this kind of yellow transparent box gives you a preview of what it's going to look once this command is accepted by you. And so in robotics, a lot of times we use 1/8 inch aluminum sheet. So I'm going to make this 0.125, which is the decimal form of 1/8 of an inch. I'm going to hit enter. You can see the preview shows, yep, looks like 1/8 of an inch. And so I'm going to hit check. And now we have a triangle that is 1/8 of an inch tall. So one of the important things to note in almost every CAD, any three-dimensional CAD software such as Solidworks, which is what we're using obviously, is kind of a method to creating parts. And the way I like to think about it is, first you create a sketch obviously, and the reason that you solely do an extrude of that sketch is, I like to think about it like you want to start with the raw material, right? And so the triangle that we have now, this triangle here, is kind of the raw material in essence. And from the raw material, you would go in with like drill holes, a mill to cut out trusses, which we'll talk about later, or talk about soon. And so you want to start with just the basic solid block of stock material and go from there. That way, if you mess up all the other drill holes and stuff, you can just delete those features and you're still left with back at the solid block of material. Now, to create trusses, once we have our solid block, and so this is also an important note, is this blue line right here. I'm not sure exactly what it's called. Oh, it's called the rollback line. And so anything above this blue rollback line is stuff that is completed. You can't access it without like clicking on it and doing some edit features, stuff like that. So it's already set in stone. It's done. You're good. Once you create a new sketch, which I'm going to create right now, hit sketch again. I'm going to select the top plane, which is kind of a standard thing. You can see this sketch is now below the rollback line. So it's not set in stone. It's not done. You can see with these two icons in the corner, these two icons mean that you're currently in this sketch working on this part of the component. And if you want to X out of it and kind of set it in stone, like I like to say, you hit this blue, no, what it's called, blue thing, and now you're out of it. Okay. So we're gonna work like again in this top plane. Get yourself perpendicular to what you're trying to do. You can see we're currently editing this part of the sketch, which is the plane I just selected. In order to create trusses, what you're going to want to do is, if you think about how I've made trusses in the 2020 robot, you kind of want to leave a certain amount of material along the outer edge. That way you have enough stiffness, and then create the triangle cutouts from there. So to create the offset, what you're going to select the line command, which keyboard shortcut L for me. You can see over here in the idea tree, we're in the insert line command, which means we know 100% sure we are going to be drawing lines, as you can also tell by the pencil icon. Select any corner, go over. Same thing we created the 2D sketch, just go along around the border, essentially recreate the sketch. And then from there, what we're going to do is what we call an offset. I highly recommend you make one of these, your keyboard shortcuts, again by going, I'll reiterate, tools, customize, keyboard, and typing in offset and making it offset entities O. Okay, make sure it's offset entities, not just offset. That'll mess you up. And so I hit O for offset. Again, we're in the offset entities command. And this number here, this 0.1, tells you how much you're going to be offsetting the sketch. Now, right now, it is a closed sketch, but it wants to know what exactly you want to offset. So after you hit O and the box pops up, you're going to want to select the outer border or whatever you're going to be offsetting. Now, all four of these kind of three, the reverse, select chain, and bidirectional, are all really important features that I use consistently when I'm trying to use the offset command, which is quite often. So to give you kind of an overview, if you only click the one line, it'll only do the one line. If you have select chain, it'll also, you can see the preview, it'll also go ahead and automatically select other lines that are connected to the one line that you've selected, which in this case we want to do. Reverse will reverse the direction that it's going to offset, so it's like offsetting inwards now. You can offset it outwards by unclicking the reverse. And then bidirectional, bi as in two, multi-directional, will offset both inwards and outwards, or kind of both directions from the line that you've selected. So for this situation, when you're doing trusses, you want to offset inwards, so something along these lines. As a general, I usually, for kind of non-structural components, I like to offset 0.25 inches. That's kind of a general strong enough basis. So 0.25, you can see the preview looks good, so I'm going to go ahead and hit enter. And we now have a new sketch of a smaller triangle inside the larger triangle. Okay, so now that we have our offset triangle, we're going to go ahead and start to create the inner trusses that we're going to be leaving that material as part of the kind of structure of the trusses. So to do this, what I recommend, what's a strong way to build a part like this with trusses, is a 45 degree triangle, 45, 90 that is. So hit your insert line command, go from bottom corner is fine, doesn't really matter where you start. There's some ways to do it, but it doesn't really matter again. You're going to kind of select all the way across to this face. Doesn't really matter the angle yet, because what we're going to do is you're going to go in with your dimension feature, dimension command, hit the one line, hit the other line, and set it at 45 degrees. And now we have a 45-degree line from this face, which looks good. We're going to go in and create our other line of the triangle down here, dimension it, and make sure you have 90 degrees to complete the triangle. Now, you can see kind of with the outside border of this piece, we have what you can kind of visualize as material that's going to be left away. So we have a border of material. Once what we've just done, we've created a triangle, yes, but it's not material that we're going to be keeping, because right now it's just two lines, which it won't really work. So you need to create thickness of these, of the triangle, essentially, is kind of, I'll show you, it's a little hard to describe. So to do that, we're going to offset this line. Again, you can see we don't really want to offset the whole triangle, we just want to offset this one piece. So turn off select chain, 0.25 is good enough. Hit enter, same thing with this one, hit enter, and you can kind of see it does a little bit of a sloppy job. It's not that intuitive, where you can see there's a little bit of extra line up here, down here, and over here. It didn't complete the line all the way through on this bottom half. So first thing I'm going to do is complete the line, so hit L for line, and go down here. And what you can see is this kind of yellow grid snap shows me that I'm going to be perpendicular with, so you can see 45 degrees next to the pencil too. That means I'm going to be in line with this line up here, because it kind of snaps to it. So, oh, why do I have a circle command? That's weird. So once it's snapped, the yellow preview line is in line with the other line. And then also you see this orange bottom line right here. The orange means that you're essentially touching the line. So right now it's not orange, you touch it and it is orange. And you want it to be orange. You want to be a complete enclosed triangle. So once it's orange, you're all set. Now to get rid of this extra length of the line, we're going to do a command called trim. Again, I recommend that you put trim as one of your keyboard shortcuts. I use it all the time. It's extremely important. If you don't have it set yet, go into tools again, but trim entities is also right here. And what you do is you kind of get inside your shape. So I want to start by trimming this extra length right here. I'm going to go next to it, left click, and drag across that line and release. And that'll, again, left click, drag across, and release. And it'll trim the part that you don't want. And then also you can see right now we have kind of what we're looking for. So we have the outer border that we're going to keep, and then also this kind of inner part right here that we also are going to keep material from. But there are these kind of little line segments here that kind of disconnect the outer border with the inner parts. So I want to get rid of those. I'm going to go to trim and go across and get rid of those. Now it's really simple. It's really easy to see. The lighter parts we're going to keep material, and the dark parts we're going to be what they call cut extruding. Okay, so once we have this all sketched up, we're going to, like I said, go into the cut extrude feature command. What that means, kind of as the name implies, we're going to be cutting, kind of extruding, but the reverse way. So we're going to be cutting out material. So go ahead, go into features, hit extrude cut. You can see we're in the cut extrude command. And right now I think we want to cut extrude the outer part, which is not what we want to do. We want to be extruding the inner triangles. So go ahead and click the inner triangles. It'll select them for you. You can see the preview. And we're going to be doing kind of what they call a through cut. So we're going to be cutting all the way through the material, the full thickness of the material, not halfway through like it currently is. So in order to do that, hit the little drop down menu and hit through all. And now we can see with the yellow preview box, we're going to be cutting all the way through the thickness of the material, all the way through. Once it looks good, hit check, and there you go. We've got kind of our general, or I guess more defined triangular shape that we're going to be keeping of material. Okay, so the next step, once we've had our piece kind of cut out rough, is understanding kind of the strength of materials, and you can kind of learn this over time via working with robotics and manufacturing parts. It's in textbooks. It's kind of just something you pick up over time, and that is that corners are very, very bad. They are, if any part of this component were to break, it would be at the corners. That's where all the, so if you have like, say this corner for example, all the force that's being transferred through this beam and this beam all converges onto this one point of the triangle, which is where it would most likely crack if you're putting any sort of force on it. Um, and so I can show you that. Actually, I probably should. I'll show you that in a simulation. And so to show you what I mean by corners are bad, I've done this. Excuse me. Done this quick SolidWorks simulation, which I'll tell you guys how to do a little bit later on. Pretty much I've exerted a force in this direction, and what you can see from this data is the darker like red colors are where more stress, more strain is applied on the material, and you can see kind of the greens and reds, the worst amount of stress is applied at each of the corners. So like to here, that's red, green, green. So you can see just in this quick simulation that if anything, any part were to break, it's where it's going to take the most amount of stress, which is at the corners. So in order to kind of mediate this issue, what we do is we put something called a fillet, which essentially is rounding those corners, because if you put more material on those corners, it's going to be less likely to break in that area. And so once again, I've made fillet a keyboard shortcut. I've made it F for me because I use it all the time. So I've hit F. I'm now in the fillet command, as you can see, and it automatically generates a kind of curvature fillet, which you can see in the preview, where it rounds off the corner. So I'm going to go ahead and make sure you're selecting only the corner, not like the face, or one of these edges. You're going to select just the inside corner of the triangle, all the way around. It can be a little bit time consuming, but this stuff is very, very important to do. Go around real quick, select all these inner edges. You'll get faster doing this stuff if you're slow at first. Feel free to pause the video and do it on your own time. So now you can see I've previewed every single corner. Every single inside corner is previewing a fillet. You can change the radius of the fillet as well as some other features, symmetric, all that kind of stuff. Don't worry about that. So generally with a small part like this, 0.1 just kind of based on the way it looks pretty good. I'm gonna drop it to 0.075. That's probably, oopsies, 0.075 is probably good enough. Hit enter, and now we have rounded corners in all of our triangles, which you'll see definitely a lot more on the parts that I've made into 2020 Robot. That's on every single part I've ever made because it just makes it so much stronger. And so that looks pretty good. Looks like a finished part. And so one of the things you can run into a lot of times is you make a pretty good looking part like this, and then you end up putting it into like the full assembly of the robot, and you realize, oh shoot, I actually need a hole, at some location on this part, but it's already all done. And instead of having to go back, so what you can do as an option is in your idea tree over here, whatever they call it, you can go back in, click the drop down for cut extrude or whatever feature you want. Click sketch, right click and do edit sketch, and go back in and do circles, and things are kind of messy when you try to do that. So what I like to do is kind of like totally get rid of the fillet, the cut extrude that I've done, which isn't a big deal. So you just do right click, hit delete, and we did kind of jump back a couple of steps, but it's what happens in the design and iteration process where you go in, it's not right, and you have to redo it. And it's a lot easier to do it here in CAD than machine the part incorrectly and then having to kind of remachine it later on once you realize, get it in hand that it's not right. And so I'm just going to go back and to edit sketch. And a lot of our work's already, like, it's already in here, it's not a huge deal. Say we want to put a circle hole for a bolt or whatever in this bottom corner. First thing you want to do is lay out where you want that circle to be. So say I know I want the circle to be offset from this face 1/4 of an inch and offset from this face 1/4 of an inch. I'm going to hit offset, do 0.25, and what you want to do is, so you can hit enter, but when you're trying to just kind of lay out where you want holes to go, or kind of envision things in CAD but not officially drawn, you can hit this thing called for construction under options, and that makes the line dotted. And and it kind of won't interfere with like your other triangles that we've drawn here. It's kind of just like on the side, not officially drawn. So I'm gonna do the same thing for this bottom line, hit enter, go in, and make it full construction. So now we have kind of a check mark of where we want the circle to be. So I'm gonna hit C for circle. Again, we're in circle command. I recommend you make that a keyboard shortcut. Right on the hash mark, put a circle. Go in with your dimension tool, like this. What the? There we go. So it's a little laggy. And dimension it for maybe like a 0.2 bolt or whatever it might be. So now we can see we want a hole to be there, but we have an issue, right? Because we're keeping this outer border of material, but now we're cutting into our cutout triangle, which is, it's not going to work. So what I do is I create a new circle around the same place, and I'm trying to envision how much material I want to keep around this hole. So actually, I'm going to do an offset instead, so because I know I want to keep 0.25 inches of material. So I'm going to offset the edge of the circle 0.25, hit enter, go in with trim, and trim around all the excess stuff that we're not going to end up needing. And so you saw what happens here. Again, the software is smart. Once I kind of get rid of this command, it kind of goes all red and yellow, which again, back from previous videos you saw is what they call unsolvable, not good. So just don't do that. Don't worry about it. It's fine. Keep it the way it is. It's a little bit more work, but it's not going to totally screw up your whole design. Okay, so now we have the circle defined. We're going to go back in, kind of retracing our old steps that we end up having to delete. So first thing we're going to do is go back and do cut extrude. We're going to select the new things we want to extrude, which is going to be these triangles, as well as the circular drill hole. Everything in the preview looks good. We're going to make sure we're doing, again, through all, and hit check. And now we have a circular drill hole in our piece. When I go back into fillet, this part kind of stinks. I do it all over again, but you'll get faster at it. So if you make a mistake, I just made a mistake, click it, hit delete. Make sure you've only got the inside corners of the triangle selected. You can go right around here. Select all of this part. And preview looks good. I'm going to hit check. If you hit check and you realize, oh, I missed a corner, don't delete the whole thing. Just click on it, right click, hit edit, and you can go ahead and, you know, add other corners that you need to add, and it'll just do it right for you. Okay, so that's good. And now the part looks pretty finished. It looks really good. Everything's laid out correctly. And so last thing we're going to talk about is editing appearances, which I usually do. And I'm trying to do like full CAD models, full assemblies of the entire robot. I want it to look good. So say we're making this part out of, you know, black plastic, and I want it to look realistic. I'm going to go hit this little appearance color wheel tab, right click under this blank open space, and hit add appearance. It automatically pops up, already defined as part 1, which is just the part that we have right here. So that's already set. You can quickly select, you know, black, green, pink looks dope. We're going to do pink, you know, why not? And then you can go also into advanced settings, illumination, and kind of adjust like how bright the color is. That's more darker, that's more lighter. How transparent it is. If you're trying to model like polycarb, which is clear, you can make it more transparent. You know, all that kind of stuff. That looks good to me. Nice pink part. We can kind of go from there. Okay, so once you have a part, you're going to want to save it. If pretty simply just go File, Save. I'm going to name it, maybe we'll do like Test Part 1 is fine. I'm just going to put it in my personal, create a new folder called Test, just call it Test, whatever, that's fine. And save it under there. And we're all set. Now what we're going to be doing today is creating kind of a full assembly. An assembly has multiple parts. And so the next part we're going to be creating is somewhat of a dowel. So I'm going to go over here, do File, New Part, and the same process that we did before. Documents, units, make sure you're in inches, hit OK, settings, sketch. We're already on the front plane, so that's good. And now we're going to create somewhat of a hex dowel. So to do this, we're going to first create the hex part. There are these 9 boxes up here with all different things you can use to help you along. So you got circles, curves, and hexagon, or rather polygon, is one of the really important ones I use for making hex shafts, which is what we use in FRC a lot. So just kind of create the general shape of a hexagon. You're going to want to say hexagon or an octagon? Oh god, not hexagon, which one? Oh my goodness. Dimension this. We do 1/2 inch from side to side hex shaft, all of FRC for the most part, so 0.5. Now we have a 0.5 inch from side to side hexagon. We're going to be extruding it, so E is a keyboard shortcut. We're going to extrude it maybe 3 inches, and now we have a nice hex shaft. And like we previously said on the previous part, this is going to kind of interlock with the pink piece that we made before, and it's going to lock in with the bolt holes that we made that were 0.25 or 0.2 outer diameter. So now I'm going to create a new sketch. You can, if you want to, just hit sketch here, select this top plane, C for circle, dimension it 0.2, hit extrude again. Our pink material was 0.125 inches thick, which looks great. I'm going to do it on both sides. Repeating the process like I said. And you guys will get really fast at doing this, and it'll become kind of second nature, like I have. Oh, made a mistake there. I definitely made a mistake. I'm going to go back in, edit this. Looks like it's the wrong size. Yep, 0.2. What on earth? There we go. 0.2. And now we have a nice dowel. Pretty simple. Now I'm going to make this part a different color. To kind of differentiate, we're going to make this one black. Hit check. Go up here, go to File, Save. Dowel. Let's call it Connector. I can't spell for the life of me, it doesn't really matter. And like you saw, I saved it under the same kind of file, the test file folder that we put our first part into. So now we have 2 parts, which is kind of the beginning of what an assembly can be. Okay, so now we have 2 parts, like I said, which is what an assembly requires. It requires more than 1 part. To create an assembly, which again is kind of a compound of many different parts, or maybe just 2 parts, whatever it might be. When you go File, hit New, and select double-click on Assembly. And you'll see the assembly interface a little bit different. So right when you open it, it asks with the Begin Assembly kind of pop-up menu. Essentially what that means is it wants you to define what the base of the assembly is going to be. And so whenever you make an assembly, you kind of want to, the first thing you want to put in the first part you want to put in the assembly is a part that's not going to be moving. So for FRC, I like to make it kind of like the drive base, or, like at least a wheel of the drive base, or, the first frame piece. That's not going to be, things will be built up upon that, right? It's kind of the foundation. So for us, I'm going to make that test part number 1, which is our pink frame here. Just kind of click on it, drag it in. And now this part is in our assembly called Assembly 1. And assemblies is really kind of 2 or 3 main features that I use for FRC in assemblies, which is why they're pretty simple, honestly. The first one is move and rotate components, which we only have 1 in, so it doesn't really help us. Mate and then insert a new component. So now we have one component in here. I'm going to insert, so just left click, insert, and so this window will pop up, and that shows you all the different tabs that we have open. So right now we have the connector tab open. You can go and see, oh, sorry. You can see those two are kind of in the pop-up window, which means that we have them in another file already opened on this desktop. So I'm going to insert that one. So if it's not there, right, if you need to insert something that's not there, you can just hit browse, go into like your files, and hit whatever file you need it to be. But we already have it already in here, so that's simple enough. I'm going to put it in. This is what I was talking about earlier with kind of selecting your original sketch planes, thinking in advance. I did not do that. I usually never do. I'm kind of just too lazy to think about it that far in advance. So I made both of these on the same plane, so that they're both kind of oriented in the same way, which is not how I want them to be oriented in the final assembly. So to fix that, so what I'm trying to do essentially is I'm trying to put this nub into this hole. So to do that, because if I try to do it right now, it might work, but it's kind of sketchy. So I can try to do it like this, and it's not what I want, right? So I'm gonna try to do rotate component. Just simply click and drag, and it's kind of like a really free click and drag. It's kind of gotta move it until it looks right and it looks good enough. So that right there looks good enough to me. We're kind of in line with how we want it to be. And so the next important feature, the biggest important feature of an assembly, is called a mate. And what a mate is you're joining two surfaces. They can be curved, they can be flat, doesn't really matter. You're putting two surfaces together. So in this case, I want to put together the outer ring of this dowel and the inner ring of this drill hole. So I'm going to hit mate. It's going to ask you, the blue box is kind of what you're currently working on. So right now, the blue box is around mate selections, which means it's asking you to select which surfaces you want to mate together. So I want to mate this outer one with this inner surface right here. And the way mates work is right now it's concentric. So only one singular mate, like I've done here, is not going to put it exactly where I want it to be. All it's doing is it's concentrically, so it's circularly, concentric is circle, it's concentrically mating these two surfaces kind of, in line with each other. So that's kind of where you have to start, right? And so we've done one mate. You hit check. The mate command is still open. If you don't want to open, you can simply hit escape. Escape always backs out of whatever you're doing. Re-hit mate. And what we want is we want this face to be mated with this face right here. So I'm going to go ahead and select this face. Select this face. You can kind of see it previews it. It's moved the whole dowel assembly out to the right where we want it to be. Okay, and so Solidworks is smart enough to know that if you simply manufacture both of these pieces as they were designed in CAD and kind of stuck the black piece into the pink piece, what's going to happen in the real world is it's just going to spin, just like it knows it's going to spin like that. There's nothing you can really do. And so maybe when we were designing this, maybe we want to create like a non-circular hole that kind of locks in and doesn't rotate, or we have some future plan for it. But for just this, for the simplicity of this CAD, I just made two circles. And so what I'm going to do is, I don't really want this thing to be spinning all around here. It's kind of weird. I'm going to artificially lock the rotation of this dowel. Now, there are two ways to do it. The one way you can do it is if you kind of line it up by eye and guess, all right, I want it to look something like this in this orientation. That looks pretty good. I want it to stay just like that whenever I'm doing further mates and further things in this assembly. You can go in and select the mate that you chose, which would be this concentric mate. Right click, hit edit, and then hit lock. And what lock is going to do is it's going to lock the current position of the mate that I've selected, which in this situation is the concentric mate of kind of the inner peg and the whole of the pink piece. And so you gotta kind of be careful with lock, because it's somewhat difficult to unlock components, because the whole idea is you're permanently locking it. And so if you go ahead and are further along the assembly and trying to and you end up realizing that you don't want these two to be locked, you can run into some issues with like mating errors and things like that. So what I like to do, in this case it works out pretty well, is I'm actually going to mate this surface with this one right here, and you can kind of see it like auto rotates to be flat with each other. And so that looks pretty good. I'm going to hit check, and now you can see it's not going to be able to rotate at all anymore. So I'm going to do the same process for kind of copying this pink piece on the other side of the dowel. So insert component, test part 1, hit check, hit mate, mate the inner and the outer, hit check, mate once again, this part and this part, and bam. We got ourselves some weird looking snow plow fork cool thingamabobber. Alright? Okay, so the next thing I want to show you guys is how you would download a part or an STL CAD file from one of the suppliers of First. So for this example, we're going to be downloading a 48 tooth gear that comes from AndyMark. And those are gears that come in a lot of the drivetrains, the Toughbox mini drivetrains. And I used them on last year's robot for the hood part of the shooter. So you open up AndyMark, go to mechanical, and then go to motion and hit gears. From here you can just scroll down. This is the one that we want right here, 48 tooth, with a 1/2 inch hex bore. It's what we use for, again, what we use for robotics is 1/2 inch hex bore. And what's really important to note about all of these files, especially the gear ones, is the specifications box, because you use these values a lot when you're trying to incorporate these parts into your models. So for this gear specifically, it has a diameter pitch of 20, which just means that for every inch of circumference, there is 20 teeth. And then the other important thing to note is the pitch diameter, which is right here. And pitch diameter is it's kind of like a diameter of the gear, but they call it a pitch diameter because it's not all the way from the outside to the inside. It's actually a little bit different, and I'll show you what I mean by that. So pitch diameter, you can see here, it's kind of it's really halfway between, so like the gear teeth have a parabolic arc from the bottom here to the top here, and the pitch diameter kind of cuts that in half. And this is really important because when gears interlock like this, you want the pitch diameters of each of the gears to be kind of like tangent with each other, right? So the pitch diameter of this gear is this dotted line, and this one is this other dotted line, and they have to be tangent to each other. So that's really important. Okay, so to download this gear, it's pretty simple. You just have to go under this CAD files section right here, and click the STL. It'll download on the web browser. You can then double click, and it opens right into the SolidWorks part file. They usually, some errors will pop up like this. It doesn't really matter. Just like hit OK and keep on going. It'll pop up eventually. These do tend to take a little bit longer to open. I don't know why. They are STLs instead of like part files. And the difference is an STL, you can't really edit the part easily, but you can take dimensions off of it, right? And so you can see it looks a little bit different. In the idea tree, there's not like any of your extrude stuff or sketches, all that kind of, it's kind of just like a solid body. But what you can do is make sure you're in inch pound seconds, which is good. And then you can go in, sorry, and you can still kind of take dimensions. So if you want to, you can like roughly take the pitch diameter, all that kind of stuff. But it's not as accurate as taking the pitch diameter just from the website, which is what we're going to be doing. So then you just want to go File, Save. That's fine if it's an empty sketch, and then save it as like 48 tooth 20 diameter pitch. And so I was saying what diameter pitch was. all of first use, I think so actually. I think all of the gears that first uses is 20 DP. All the motors use that, all the gearboxes. It's kind of a standard, but it's still like important to know. So 48220 DP gear, and I'm gonna save it under my 4 GB file under hardware, and hit save. And that's all set. You can close out of that. Close out of this. So now it's 2 of them open. Just like close the other one out. Doesn't really matter. And then we're going to insert this gear into our assembly. So insert component. We're going to go browse 4 GB red, FRC model, other. And so this is kind of the issue is, right, files can easily get lost kind of wherever you put them. Which actually, did I even put it? No, I put it in hardware, that's why. So right there, open it up. Again, we want it to kind of go on this hex shaft. It's oriented the wrong way. So we're going to rotate it roughly to where we want it to. And now for mating hex shaft to hex shaft, you probably use it a lot whenever you're doing CAD. You pretty much need to mate 2 of the faces of this inner hex of the gear and 2 of the faces of the hex shaft, and they need to be faces that aren't opposite each other but are kind of like next to each other, right? So I'm gonna mate kind of this bottom face roughly lines up with this one, and then this side face that's next to it lines up with this one. And then for now I'm just gonna slide it down. I don't think the mate for this one's stuck. What the heck? Okay, there we go. And then I'm also going to insert the other half of this pink piece right here, which was personal, test part 1. Insert it in, mate those 2, mate this and this. And now we're all set. So for the next components I'm going to be making, I need to open all the, like what I like to do is I like to open all the files, the kind of like pre-made files by Andy Mark or Vex, open them into Solidworks so I can reference all their dimensions when I'm creating this next part. So the 2 things we're going to need is we're going to need a smaller one of these gears right here that is going to mesh with this gear, and then we're also going to need the kind of pulley for the belt that we're going to be putting on here. That's also going to go on the same axle of the smaller gear. So I already have them downloaded, but I'm going to go in and show you guys how you can do that. So go back to mechanical gears. We're going to be interlocking that big gear with the smaller gear, because we want kind of a ratio, a gearing ratio, so that we have more torque on this piece, because that's kind of what you generally want to do in robotics, is for small things create more torque. So let's go with maybe, how about a 20 tooth? That should be fine. Download the CAD file. Again, they give us diameter pitch, which is 20, and pitch diameter, which is all the stuff you're going to need. It'll give you errors, just hit OK, load SolidWorks, all that kind of stuff. This is loading up. Don't run diagnostics, it's kind of useless. And here we go. So we got a nice gear. Gonna go file, save, 20 tooth, 20 DP gear. Save it in the same place as the other one. FRC hardware. Save. You can X out of it. Again, I opened 2. Just get rid of it. Don't save that. And then we're also gonna need to open our pulleys. Spelled pulleys wrong. Okay, so they're in Vex Pro. We we want the GT2 as a kind of standard, and we want the 9mm wide belt. So I should do a timing belt rather. And we're gonna download the 18 tooth. Go into CAD files on at the bottom here. Download the 18 tooth and download the 36 tooth. Should be okay. Open both those up. And we're going to do the same process of saving them as files. Okay, so once we have all of our gears open, we can go ahead and save them all. Same process before. So you can already see 36 tooth, 15mm wide. Oh, that is not what we want. Okay, so make sure that you downloaded the 36 tooth and 9mm wide. 9mm isn't as strong as 15mm. 15mm is generally used for the drive base, and 9mm is used for kind of smaller stuff, a lot of game manipulators, stuff like that. So make sure you downloaded the right one. I did not on the first try, but that's okay. It's how you learn. Get this opened up. The 18 tooth one we can save right now. Believe. Save it as 18 tooth, 9mm wide pulley. You can save this one too. 36 tooth, 9mm wide pulley. Personal hardware. Save. Okay, so I've gone ahead and inserted all of these belts, pulleys and gears into the assembly. You don't have to do that yet. I was just gonna show you guys what we're looking for in the future. You can see there's a lot of yellow and red things. Those don't really matter. That you're gonna have them all over the place when you're creating big assemblies. They don't really matter. It's fine. Just ignore them for now. But while I have this here, I kind of want to go over two things. One, some of the features of an assembly that you can do, as well as kind of what a gearbox or a two-stage gear ratio looks like. So right now we have these gears and pulleys assembled in what they call a two-stage assembly. So as you spin this smaller gear, it'll be attached via belt to this larger pulley. It'll be attached to this larger pulley, and it'll spin at a slower rate, which is linked to this smaller gear via the axle. And once this smaller gear is spinning, it'll spin the larger gear again at a slower rate. And so these are assembled in a two-stage because you have one stage here on the left, and another stage here on the right. And when you have them aligned in this two-stage kind of system, the ratio of the gears of pulleys are actually multiplied, right? And so we have an 18 tooth and a 36 tooth. So this larger gear is going to spin at half the rate, 1/2 the rate of this smaller pulley. And this one, which is a 20 to 48, is going to spin again roughly at half the rate. So we have 1/2 and 1/2. And when they're arranged in a two-stage gearbox, you actually multiply those two ratios together. So 1/2 times 1/2 is 1/4. And what that means is this larger gear is going to be spinning at 1/4 the rate of this smaller gear. So if you had these all aligned in like a one stage, for example, it would probably only spin at half the rate. But because we have a two-stage, this smaller one's going to spin. So 4 revolutions of this smaller one is only going to be 1 revolution of this larger one. And what that does is a couple of things. First of all, yes, it spins slower, so you have a little bit more control of how fast this thing is spinning. And you also get more torque. You're going to get 4 times as much torque, because it's 1/4, 4 times as much torque on this end assembly here 4 times as much torque as you do just from the output of the motor attached to this smaller pulley. Which, when really, if you're trying to lift like a heavy part, for example, or some component that's really heavy, you're gonna want a ratio probably even more than this, more than 1/4, whether it be like 1/6, 1/8, something along those lines. So you can get more torque and therefore kind of more force to lift the game piece that would be like on the end of this component or whatever it might be. And so some of the features I'm going to go over right now, assembly features, are things I use when I'm creating large assemblies. And the thing, SolidWorks isn't really made to be creating large assemblies. There are other softwares that are better for creating large assemblies. And the reason for that is once you get a lot of components in here, so the robot from 2020 was like over 1,000 components. We only have 1, 2, 3, 4, 5, 6, 7, 8 components in here. But once you get more and more, it'll start to slow down the performance, it'll start to get laggy, and you just don't want to be dealing with that while you're trying to work inside this assembly. So to mediate that, one of the best things you can do is go into View, Display, and right now it's shaded with edges. If you just make it shaded, you can see all the edges kind of disappear, but that's kind of a way to optimize the assembly and things won't lag as much. So once you get over like 100 components, generally I like to kind of take away those edges. It doesn't look as good, but it's a lot faster. The other things you can do is go into Settings, Document Properties, and go into Image Quality. And right now I have these two settings kind of control how highly defined the objects in the assembly are. So you can change the knob and you can kind of see the circle becomes like only a couple lines to like more and more and more until eventually it becomes like a really nice circle, but that slows down your performance. So if you lower these down, both these down all the way, you're going to get a lot better performance. But for now, I'm going to keep it right in the middle. And so the other thing you can do, two features that I like to use, is what they call hide component and change transparency. So if you click on one of the objects you want to hide or make transparent, you can click on it, right click, and this little icon, the eye icon here, hide component, will totally get rid of your component. You can tell in the idea tree now it's kind of like a white object next to the part, which means that it's being hidden. If you want to bring it back, you can simply right click and do show component. You can also click on the component, right click, and do change transparency, and that kind of makes, in this case, our pulley transparent. And sometimes I do this, I either hide the component or make it transparent when there's a lot of components in kind of a small area and it can get kind of confusing. So if you want to hide the components or make them transparent, it simplifies what you're looking at and makes it a little bit easier to understand. And to bring it back, simply right click, change transparency again. Okay, so what I've done here is I've drawn circles, as you can see here, in the gear sketch, in the gear parts of the pitch diameter that the AndyMark gives us. So you can see I drew a circle in here, 1 inch diameter. That's what AndyMark has for its pitch diameter for this gear, and same thing for the larger gear too. And so the reason I've done that is to help visualize kind of how these gears are going to mesh. So you can see here, these are the circles that I drew again, and like I previously mentioned, you want the pitch diameters of these gears to be tangent to each other. And what I mean by that, which you can now more clearly see, is you want the pitch diameter of this larger gear to be tangent with the pitch diameter of this smaller gear, something along these lines. And so what we can now see is that if we're trying to make these gears mesh correctly, we're going to need to make a plate like kind of across both these gears, and we're going to put holes in the center of these two gears. And now we can see the way we space these two holes out is you do the radius of the pitch diameter of the larger gear, which would be from here to here, plus the radius of the pitch diameter of the smaller gear, which would be from here to here. And together those will create a line from here to across here, which will be correctly spaced to mesh these gears correctly. So the pitch diameter of this larger gear is 2.4 diameter, so half that's will be 1.2, plus the radius of this one's going to be 0.5, so it's going to be 1.7 is going to be the spacing for a plate to join these two gears together. So I'm now going to go ahead and start to make this plate that's going to connect these two gears and kind of house an area for these two pulleys, as well as a motor to drive this smaller pulley over here. So I'm going to create a new part like we've done many times already. Go ahead into document properties, units, make sure we're in inches. And the first thing that you're going to always want to do, I now have Sketch open, is you're going to always want to lay out the kind of more complicated components of the plate, right? So in this case, in most gearboxes and things like that, you're going to want to lay out where the gears are going to go first, and then create the plate around those dimensions that we now have with the two gears. Same thing for creating a lot of the, subsystems, intakes, shooters, all that kind of stuff. You're going to want to lay out the important things such as where the wheels are going to go, the spacing of how kind of the game piece is going to fit in that intake or whatever manipulator you're going to have. So first we're going to start with our gear, which we know is a 2.4 pitch diameter. And just to kind of lay things out, I like to make things first in construction mode, and you can always kind of go in here and change it back to a real line if you want to. But for now, I'm going to keep it construction. And then, like I previously mentioned, we know we're going to need to do kind of those two radiuses of the two gears combined to mesh them correctly, which was 1.7 inches. Again, make it construction. And now we can draw the smaller gear, which we know has a pitch diameter of 1. And everything checks out because you can see the pitch diameters are tangent, they line up, everything looks good. So we can now create our plate to kind of around these components and stuff, and make holes to mount these gears around our kind of construction sketch that we've now made. And we'll also need to put in the kind of smaller pulley that's going to house the belt. Doesn't really matter how far away it is for this situation. If you're making an actual component, you might want to kind of see where this component or this subsystem is going to fit in your robot. But for now, we'll just put it, let's say, 2.5 inches away from this axle here. And so this locker jig represents the gear on our current assembly, which is the 48 tooth gear. And so we're going to need to put a bearing on the hex axle that we have. And the outer diameter of a bearing, which we can reference in the part file of the bearing from Andy Mark, it's a 1.125 inch outer diameter. So I'm going to start with that hole. We're also going to need a hole for the smaller gear, which again is going to be the same 1.125 inch dimension. So now we have our bearings set out. Next thing we're going to do is offset these, right? Because we're trying to, the same way we made the original plate, you want to have your holes, and then you kind of want to create a border around those holes of material that you're going to be keeping. So for a component like this, I'm actually going to do an offset. So O, I'm going to offset it 0.375, 3/8 of an inch, which is probably good. Same thing for this one. And now you can see with a little trim, we're going to be keeping this outer border of material to house the bearings. And then we're also going to put in another one over here for the small pulley. Again, 1.125 for a bearing. So we're going to have 3 bearings laid out, and also offset this just for now to make sure we have enough space in this whole assembly to fit all the bearings and enough material around the bearings. It'll be a strong enough part. Okay, so I've gone ahead and pulled up the motor that we're going to be using for this assembly. I quickly went to Andy Mark, searched gearbox, and it pops right up, this 57 Sport. We're going to do a 2-stage gearbox, so we're going to download the CAD file. I'm going to open it up in SolidWorks, and we're going to proceed to save this file under whatever folder or on whatever flash drive you have for like hardware stuff. So open this up. And the reason we're doing this is because we need to get a lot of the dimensions from this gearbox such as where the mounting holes are positioned. That way we can effectively mount this motor. So here it is. I'm going to right away save it as 57 two-stage gearbox. Save it under this FRC models. Hardware is fine. And there we go. So to get the mounting holes, it's pretty simple. Once this thing stops loading, I can show you what to do. Alright. So we're going to get our view again perpendicular to what we're looking at. And these are the mount holes that we have. These 4 mount holes. We're going to mount this gearbox with all 4 of those holes. So we're going to do... we're going to just hit the line command and automatically edit sketch will pop up. We're going to select this plane to sketch onto, which is just kind of the plane of the front of the motor casing. And we're going to just simply go across and make our square. We're going to make sure this documents in units, inches, which now it is. And then we're going to see what dimensions we have. So what I'm actually going to do, what I'm actually going to do is kind of create a template for ourselves that we can then go ahead and go over this, do control copy. It'll say some of them can't be copied, just hit yes, that's fine. Now we have a sketch of the mounting hole layouts that we have now copied. We can go back into our sketch, and we're going to be mounting this right on this bearing that we've created for ourselves. So hit Control V, and then we're going to do, we want this hash mark right in the middle to be lined up with center of the hole. So we're going to move entities, left click and drag downwards to copy them. Our start point is going to be in the middle. We're just going to click once, move our cursor until it kind of, you can see it kind of clicks in, and then left click again and right click. And now we know we're going to mount the motor, the gearbox, with these 4 points right here. Okay, now we have our mounting hole locations. So we're going to go ahead and kind of lay out what material we're going to be keeping from these. So first thing I'm going to do is actually make this fully, so I just kind of left clicked and dragged over this entire rectangular area and made it for construction. We're going to go ahead, we're going to mount these with 0.2 diameter bolts. So go ahead and create the 4 circles at each corner and dimension them all for 0.2. You guys will get really fast at this, so don't worry if it takes you a while. Once you've done that, we can then do an offset for these mounting holes. 3/8 of an inch sounds pretty good to me. Go ahead, offset all of these 3/8 of an inch. And now we can see we're going to be keeping all this outer material here too. So now everything's set up, kind of what material we're going to be keeping around the mounting holes we're going to be using. And so next thing we're going to do is kind of connect all these holes to make it one solid piece. That's going to form the whole part pretty much. So let's go ahead and just connect this outside part here. And it's going to look messy, right, guys? It's not going to look pretty by any means, but you'll see it'll kind of clean up nicely. So go ahead, connect all these just like that. The next thing we're going to do is, so now we have a bunch of lines here, a bunch of circles. We kind of have to decipher which parts we're going to be keeping, which parts we're going to be not extruding and all that kind of stuff. And so in the previous original part that we made, we kind of, like I said, start with just the stock material, which works for most of the time, but sometimes it's actually easier just to lay everything out and extrude almost the final part. And so we're going to kind of go ahead, trim things and clean them up, keeping in mind what parts we're going to be keeping and which parts we're not going to be keeping. So we're going to be pretty much only extruding everything except for the 4 mounting holes and then all of the bearing holes, which I actually just got rid of. So I have to redo that one. There we go. Just get rid of all this stuff. You can go ahead, click and delete lines. You can click and shift to select multiple things. Actually, for this one, I'm going to go like this. And just keep on trimming all along. You can see I trimmed a little bit of the bearing circle. That's fine. We'll go back and draw it back in. But this looks pretty good. Oh, oopsies. Control Z always fixes things. Go ahead, come in like this. Make sure everything's shaded in. So you want the whole circle to be shaded in. That means it's a closed contour. Go back and draw this in. And now we can more clearly see that we're going to be keeping the 4 mounting holes in the middle bearing hole. Okay, so now we can clean up this side of the part over here too. Just getting rid of all this excess material. So if you have like extra construction lines, because they're construction lines, it's not going to affect what we're going to extrude or cut extrude, because it's kind of just reference things. But non-dotted lines like this will mess you up. So make sure you get rid of all that. And now we can pretty clearly see we're going to be extruding only this white part, which will be the material that we're going to be leaving, and we're going to be kind of not extruding the other circles for the bearing holes and things like that, right? So go ahead, hit E for extrude, click the part we want, and again we're going to be extruding it 0.125 eighth of an inch for our 1/8 inch sheet metal of aluminum. And now we have a pretty decent looking part right here. We're going to have a bearing hole here, here, and here. This one will be for the gearbox. This one's going to be for the smaller gear. This one's going to be the larger gear, which is going to connect to our original component. So we can go ahead and save this maybe as test frame part 2. Save it as a part. And we're all set. I'm also going to change the appearance. Make it hammerheads blue, because why not? It's kind of aggressive, so I'm going to make it a little bit darker. And we're all set. Go back and make sure we saved it. And this kind of brings us to the next important part of assemblies, which is if you want the robot to actually kind of move and interact how it's going to be. So say you want, like for a 2020 robot, I wanted to make sure I could test the range of motion of the intake flipping up and down. So in the CAD file, I wanted to be able to physically move the whole intake assembly up and down on the robot. And what that is you have assemblies in assemblies. If I were to just insert this component into our assembly, you'll be able to move any of the parts. But if I create a separate assembly and then insert it into this assembly, I'll be able to have jointed parts that can move relative to each other. And I'll show you guys what I mean by that. So I'm going to do File. I'm going to go New, Assembly. And even with assemblies, you guys should kind of make sure that you're also in the correct units. Just because you never know if you're going to need to draw something on the assembly. So I'm going to go Assembly, Insert Component. Again, you always want to insert the first part you should insert should be the one that's not going to be moving relative to your other pieces. So that's going to be our main frame part of the assembly, which looks like this. Then I'm going to be inserting the bearings, the axle, the gears, and all that kind of stuff that attaches to this component right here. I believe AndyMark might sell hex bearings. Let me just quickly check while I'm already on their page and see if they actually have CAD files for them. They do. All right, so to go ahead and download this CAD file for the bearing. I already have it, so this isn't going to be very useful for me, but for you guys, you still need to download it. Get rid of this, hit OK. And that should be loading in the bearing, yep. Just taking a little bit of time. So you guys can go ahead and save this file save as just hex bearing, whatever you want to do. I already have one, so I'm not going to save it myself. So let's go back, open up our new assembly. That's the part, just kidding. There it is right there. We're going to insert component, find our bearing that we just saved as the STL. For me, it's under hardware, hex bearing. Go ahead and open it up. We're going to need to rotate this to be in line with the holes that we have. And then hit mate. I'm going to be mating this bearing into the hole. So first do concentric with this kind of outer ring of this bearing and inner hole of our plate. And then also you're going to want to mate this kind of face of the bearing with the outer face of this plate. And we have one bearing installed. If you don't want to go do insert component and kind of find it again, you can click on our bearing in our idea tree, right click, hit copy. It was Control C for control copy, and then Control V. We'll do it twice, and kind of do these mates again. So you guys can see that this one concentric with this one. That one goes there. This face on here. Oh, that's not what I want. This face here. Now we have our three bearings. And we're going to need to copy and do the same thing for the other side of this bearing plate. Okay, so now we need to copy this whole plate assembly and kind of copy the whole thing and then reflect it over to mirror what we have right now. So insert component, test frame part. We're going to get our bearings, copy them, paste them 3 times, rotate them 180 degrees to mirror what we have on the other side. And then mate them all to their corresponding holes. And this is tedious, but it's just good practice, and it's kind of how it goes in CAD. Things are very tedious. But you guys, again, will get faster at it, and it'll become simpler and simpler as you get more practice. Alright, this is the last one. And then we need to kind of make these in line with just this. Right now it's way above. We need to make sure it's in line with this original kind of component part here that we originally did. So the best way to do this one would just be to kind of mate in line the mounting holes. So mate this hole with this hole, which brings it down. And then mate the one diagonal to it or next to it, doesn't really matter. And now we have them in line with each other. And that looks really good. Okay, so next thing we're going to be doing is inserting the motor and gearbox into this assembly. And then we're going to be creating a hex shaft that's going to go into these 2 bearings right here to house the pulleys and smaller gears and things such as that. So we already have our gearbox downloaded. It should be browse, what did I name it? Something 2-stage, here it is. Open this up. Already into our assembly. Rotate it around like this. And then start by first mating the face of this piece to the face of this part right here. And then we're going to mate these bolts with our mounting holes. Rotate this around so it lines up roughly. And mate the second bolt into our second mounting hole. And now you can see, oh, I did not mate the right things. Alright, so you can see here I mated the wrong parts. I mated the face with this, and I kind of, well, it's fine. Nah, it's not. Okay, so you can see I mated this face with the plate, which is not what we want to do. I didn't realize it ahead of time. But we want this face right here to be flush with this face over here. So we can go down to mates. That was this mate right here. Hit delete. Yes. And would have now kind of realized a couple things. First of all, the motor has a bearing built in, so we're not going to need this bearing right here. So right click and delete. Delete this one too. I've also realized that this big kind of ring right here, you can see is too big for our hole. And so we need to make the whole of this plate a bit larger. So we're going to go back into our gearbox. We're going to see in our sketch, edit sketch, how big this circle is. Looks like it is 1.5 inches in diameter. So we're going to go back into our plates file, go back to our idea tree, which kind of gets like lost in the corner over here, which stinks, but there we go. Once we've gotten our idea tree back, our idea branch tree back, we can go into sketch, edit sketch, and make this circle 1.5. And exit our sketch, and you can see it automatically adjusts the boss extrude to kind of fit those new dimensions. So that's all set. You're going to see once we go back into the assembly, it's going to ask to rebuild the document. You do want to rebuild. That means that it knows you've changed one of the components in the document, and it wants to rebuild that component in your assembly. So just hit OK, and now we're all set. So now again, we can remate this face right here with this face. It now sits flush, looks a lot better, and we have enough space for this larger kind of housing of the bearing that the gearbox already has built in. You can see the hole on this side is a little bit bigger than what we want. And so you probably should, what we're going to do is kind of make like two separate plates, one for this side for the motor and the other one for the other side that can house a bearing. Okay, so to create a second plate that can actually house a bearing, we're going to need to, the best way to do it is to copy this plate and then just change that one dimension back to our 1.125 inch diameter for the bearing. So we're going to go into files, go into test. We have our, this is the blue component we need to change. We're going to go copy, paste, go ahead, open it up. Go back into our sketch, make it the 1.125 inches that we need. Save it. Go back into our assembly and delete this part right here. And insert our copy of that plate that we just worked on. And we lost all of our mates. We're going to have to remate this stuff. It's not a big deal. It's good practice. Get you guys faster at doing it. Just like this. Again, mating these lines too. And we're all set. So now we can go ahead, copy another hex bearing over here from our idea tree, paste it in, made it into our assembly. And we're back where we need to be, all right? So next thing we're going to do is we're going to start putting in the gears and the pulleys of this assembly. And so I think the best way to do that would first be to put the smaller pulley on this axle right here. So we're going to insert our 18-tooth small pulley, rotate it around to kind of get the general orientation that we need. And then start mating again. Make sure you mate two faces of the pulley that are next to each other. So we did that face and this face. Oh, that's not what I want. That's kind of weird. There we go. And the next, this is kind of a more complicated mate. So there's a mate called a distance mate. because right now this thing is free to slide back and forth. We want it to stay on the axle like it would in the real thing. So if you go ahead, pull this out, hit mate, you see an option down here. It's kind of like there's two lines with an arrow between them. If you hit that, that means you're doing a distance mate. So first select our two mate surfaces, which is that and this. And we're going to mate it a distance of 0.25. Nope, let's go 0.125. And that looks pretty good. And the next thing we're going to do is we're going to mate distance between these two plates. Actually, let's not do that yet. Because what we need to do next is create an axle to house our second larger pulley as well as a smaller gear, which is going to interface with our other assembly that we have with like the pink parts and stuff. Okay, so now we're going to make the hex shaft. So you can just do new part. Open up a new part. Make sure we have our units correct. Create a sketch. Hexagon, polygon, whatever it is. Dimension from face to face to be 0.5. And we're going to start with extruding it. Let's start with maybe 1.75 inches. Make it black because, you know, why not? File, save this as large pulley hex shaft. Save it under our test file. We can then go into our larger assembly that we've been working on, insert component, and browse for that large pulley hex shaft. Open it up, rotate it, and then start mating it to these bearings. That's that. Can then mate it to the outside edge of the bearing and the outside edge of this bearing, which is going to pull everything together. So actually, let's get rid of that mate. So Control Z for now. Oh wow, that did everything. Okay, that's annoying. Yikes. Not a big deal. Next thing I want to do actually is insert our large pulley and kind of figure out the spacing of where we want this plate to sit. So here's our larger pulley. We're going to rotate it around to be in line with this pulley. We're going to mate it on the hex shaft. This is where things can get a little bit crazy. Alright, two faces are mated. We're going to mate these two faces to make sure the pulleys are in line with each other. And then we're also going to insert the small 20-tooth gear. Go ahead and rotate this thing around. Same thing here. We're going to be mating two of the surfaces. That one looks good. Excuse me. That one as well. And then mate these two. We're going to go a distance of 1/8 of an inch. And so now we can kind of see that this hex shaft's not going to be long enough to interface with the bearing on this side. So we can go back into our file right here. Pull up the idea tree. And just right click on our extrude, hit edit. And we're going to make it 2 inches now. Hit check. All set. It's going to ask to rebuild. Yes, we want to rebuild. And now we can go ahead and mate the end of this axle to the bearing. And that looks pretty good. Okay, so now we have this assembly looking pretty good. The only thing is, with these planetary gearboxes, you really want to support the axle on both sides. So we have it supported on this side, but not on the other side. You would probably want some sort of hex coupler in between here to, kind of connect it to this bearing over here, something along those lines. But we did the same system for our intake in 2020 without supporting it on both sides, and it works pretty well. So it'll probably be okay for this situation right here. Next thing we're going to do is insert the motor. You can download it off of AndyMark or whatever motor you guys want to use in your CAD file. I'll give you guys the opportunity to go by yourself and look for a motor that will interface with this gearbox. I'm probably going to see what I have in here. I'm going to go with mini-sim motor. Might fit. That's way too big. Nope. Let's see what I have in here. AndyMark mini motor. That looks pretty good. This is the red line motor from AndyMark. We're going to go ahead, mate it with the gearbox. Do that. Mate the axle concentrically with this circle. And we're all set. So now we have an almost completed, actually it actually might be completed assembly here. We're going to save it. Save all. We're going to save it as kind of assemble. I can't spell for my life. Oh my god. Assemble. Whatever. Assemble. Test 2. Save it under our test folder. And now we're going to go back into our original assembly over here. And we're going to get rid of all this stuff that we don't need anymore if we put it into our other assembly. So delete all this. All the errors, again, don't matter. Just ignore them. And we're going to go ahead and insert our assembly 2 into this bad boy, rotate it around so that the kind of open bearing space. We're gonna be mating this axle with this bearing, these two bearings right here. So these bearings should still spin, yeah. Hold on a minute. If we want this to actuate, we're actually going to need to get rid of these bearings in this assembly. Yeah. So get rid of these. Go back to our assembly. We build. And we're going to be inserting those bearings into this assembly. And the reason for that is if we had it the way we originally had it, the bearings are kind of locked in place with our number 2 assembly. And we don't want that. We want them to be free spinning in our, kind of combined assembly, as I like to call it. So let's rotate these guys, mate them. Oopsies. Mate these guys. Now you can see the bearing will be able to rotate. So next we're going to do is mate this and this. A lot of things going on here. Let's grab another bearing, hex bearing, copy, paste, rotate it around, and mate it with this hole. And we're all set. Okay, so let's go ahead. So also you can see here we have kind of the lines from before, which are a little bit distracting in the assembly. So if you want to get rid of those, you can simply go into those part files. Uh, oh, geez. Right click and hit hide, and the line disappears. Same thing for this one. And that should, yep, so now we have no more lines that kind of distract from the whole assembly. So now let's start with mating this hex shaft to this bearing. Is it this face? I can't tell. What on earth? I'm going to start with making these parallel because this is annoying to deal with. So mate these two parallel to each other. Just make it a little bit easier for myself. And then now let's see if we can mate. There we go. Mate that. Mate that. Okay. So now things are still a little bit of a mess, but the shape is starting to form. So now what we're going to do is mate these two, distance mate them. Looks good enough. And then we're going to mate this gear concentrically, just like that. And now we look pretty good, actually. So what you can see here, what we've got going on, once you drive this pulley, it'll spin this axle with the bearings, which will then spin this smaller gear. And once that smaller gear spins, it'll kind of rotate around, essentially rotating this kind of pink pitchfork looking weird thingamabobber. Okay, so last step for this assembly here is going to be making the belt that connects this smaller pulley and this larger pulley. And the reason why I did this last is because so it kind of depends. So if you already have a belt that we've already purchased that, you know, one of the mentors has bought, and they want you to incorporate that length into your CAD, that's different. If this is like before so generally you want to kind of do it in CAD first and then buy the belt to the length that you did in CAD. And so I'll tell you guys how to find that length. And you're going to need to tension the belt anyway, so if it's a little bit off, it doesn't really matter. And so what we're going to do to kind of make the CAD of this belt, so we're going to first hide this plate so we have a better view of the two pulleys. Also hide these bearings. And hide this guy too. And now we can kind of see the two pulleys that we have. And we're going to see if we can find these pulleys on the website, which was Vex Pro Robotics pulleys. They were these ones. And they should give the specifications. Okay, they do. Can I open this up? What the heck? Maybe not. That's kind of annoying. So we have the 18 tooth right here. And it looks like for the 18 tooth, the pitch diameter is 28.65, which I'm assuming is centimeters because it's definitely not inches. Or no, it's probably millimeters actually. Yeah, I think it's millimeters. So 2.8 centimeters sounds about right. Yeah. So 2.865 centimeters. is going to be the dimension for that. So we're going to go ahead, change our units to centimeters, which we are now dealing with for these pulleys. Hit C for circle, do a sketch on this plane, and dimension it 28.65. Is that what it was? 28.65. Perfect. And so now you can kind of see this circle will line up with the pitch diameter of that pulley. Same thing for the larger one. That was 36 tooth, so 57.3 millimeters. We're going to go in here, dimension this 57.3. Is that right? My memory is horrible. Holy smokes. Yeah, it is. Okay, good. And that looks pretty good to me. Now I'm going to go ahead and connect these two. And so with connecting circles, you can kind of see here, see how like as I move around, the line stays tangent to the circle no matter which way I go. And so if you do it quickly, you kind of have to play with it a little bit. But kind of just make sure that your line is tangent to the circle you're working with. And then same thing over here. If you like a bigger circle, it's the same thing. So right now it's not, right? As I move the cursor around, it's only staying at one point. We don't want that. We want it to be tangent to our circle. So get rid of this one. Draw a line. And now we're tangent to this circle. So we can go ahead and connect it. And then we can go ahead and copy this sketch. Again, errors can pop up, doesn't really matter. Alright, so now we have this sketch saved. We can X out of this. And hide it so it doesn't look ugly. Want to do new part, sketch. Oh boy, we lost it. That's not good. For some reason it didn't copy. Not a big deal. Can go back and copy it and make sure that we've actually got it this time. There we go. And so it automatically looks like, yeah, so right now we're in, you want to pretty much keep your units in the millimeter unit because that's what the sketch is made in millimeters. If you don't want to change it to inches, it kind of gets a little bit wonky if we change it to inches. So we can go ahead and trim these. And now we kind of have the general outline of the belt. However, a belt has thickness, right? And so we're going to offset all of these entities like 1 millimeter maybe? Let me think. Uh-oh. Okay, this is an issue. So you can see on this corner right here, we kind of have like these two lines. They don't perfectly intersect. And so SolidWorks can't really understand what entities you want to offset. So if you just look around and trim it, now we have a nice closed region, which is indicated by the shaded area. We should be able to offset it now. Yes, we can. Select chain. We're going to do 10. No, we're going to do 1 millimeter, I think. Yep, 1 millimeter. We're going to extrude. We know this is a 9 millimeter wide belt. And belts are black. So let's make it black. And let's save this as test belts. Save it in our test folder. That all looks good. Go back into our assembly, get rid of this. We're going to hide the sketch. Okay, so last step of this process is going to be inserting the belt that we just made into this assembly. So we're going to go into test our belt, pop it in here, rotate it around. We're going to be mating concentrically this circle with the circle of this small pulley. Then I'm going to be mating this face with this face. Oh, I'm just kidding. Yeah, so with like belts and stuff, I've found that it's pretty hard to get like a full mate of what you want. So I kind of like finagle it, position it until it's about right. So that looks like where it would go. And then you have to go back to the mate that we just did, which is the concentric one, edit it, and then lock the mate, which is permanent. And now you can see the belt won't move at all if you try to move it. And here is the finished product. I don't know what you would use this for, but it's kind of what I do. This is an example of what you'd be making maybe next year or in the future years for a game manipulator. And what it is as you rotate this smaller gear, it's going to, via belt, rotate the larger gear at a slower rate, which will then rotate the smaller gear connected to the same axle, and then it'll rotate this larger gear, which will actuate this kind of arm thingamabobber. Similar to what teams used in 2018 with the hatch panels. Pretty much you'd drive up to the loading station with it down like this. The hatch panel would slide onto these forks, and then you would lift the forks up, which would kind of lock the hatch panel into your robot. So, kind of things like this. Pretty simple, but also for beginners a little bit complex. Okay, so now I'm going to go over some of the things that weren't covered by making that assembly. And one of those things in this video I'm going to do is going over Solidworks simulations to stress test your parts. So first thing you're going to want to do is open a file of whatever part you're trying to stress test or do a simulation for. I'm going to do the intake piece from the 2020 robot because it's kind of cool, which will be this one, I believe. Let me see. Yep. So this is the intake piece. You guys recognize it from the 2020 robot. Went something like this. And so to do a simulation, simply hit the simulation menu button, hit new study, and it automatically selects static, and static is kind of just like you're applying a static force to the piece, which is fine. You can also do like thermal, buckling, fatigue, a bunch of other stuff, but I mostly do static tests. So that's kind of the load that we're putting on a lot of the parts for robotics. So just hit check. You want to apply a material. It doesn't really matter what material you apply, honestly. But I'm going to apply 6061. That's what we use for all of the robotics aluminum pieces. Hit apply, and then hit close. Then you can hit fixture advisory. Go over here, it said add fixture. And so this thing was, so fixture is kind of where the attachment point of the piece is. So for this piece, we attached it around this hole, as well as these smaller holes too. We kind of bolted a plate onto this. So that looks pretty good. We're going to hit check over here. Then we're going to go to the next one, which is, external load advisor. We're going to add a load. And the load for this one was kind of when the intake dropped down, this part of the piece was hitting the front of the robot. So I want to do exert a load there to kind of simulate what it would be when it was on the robot. So hit check. And then we're going to do run this study. And it's generally pretty quick as long as you have a decent computer. So right now it's going through the whole process of running simulation. All right. You're going to go over here to stress. Right click and hit show or hide. You can also do displacement, if you want to. But really the best one to do is probably stress. And so because we're exerting a force on this face right here, it's going to kind of get dispersed somewhat around where we're um, um, fixing the part right here, but also a lot of where it's going to get hit. And so this looks pretty good. What you're looking for is kind of parts that are like red or yellow or under extreme loads, which there are some around the hole. That's kind of always what you're going to have. You can't do anything about that. But for the most part, this looks pretty good. And so say we had like a bunch of red around one of these corners, which means a lot of load, and that's probably where it's going to, or a lot of stress, probably where it's going to break. You could go in and make like a bigger fillet around this corner, so you put more material there to kind of mediate the amount of stress that it's going to be taking. So to get out of this kind of simulation example here, you're going to go back on the bottom of your screen, down here in the corner to hit model, and model will get you back to your kind of original part. So next thing I'm going to talk about is how to put gears, or how to like kind of put a gear into an assembly or just as a part by itself. So I'm going to hit File, New, a new part. Make sure that we're in inch, pound, seconds. And then in order to put a gear, you have to go down to this kind of like second tab and hit Toolbox, hit Add Ins Now, go to ANSI Inch, go down to Power Transmission for gears. You can also obviously select other stuff back there too, and then go to gears. And we use primarily for FRC, we use spur gears. Hit spur gear, right click, and hit Create Part. And automatically create a gear for you. And then over here on the kind of idea tree area to our left, we can go and edit all of these settings, right? And so I've already set DP, diameter pitch, which is like again how many teeth per diameter of the gear is 20. That's a standard for first. You can then adjust number of teeth. So if you want like a 70 tooth gear instead, you can hit 70 and it makes it 70 teeth. Pressure angle 14.5. Pressure angle, what that is this angle kind of right here relative to a line perpendicular to a tangent line of the gear. So you have a tangent line that goes down the gear like this, perpendicular line going up, and the angle in between those two is 14.5. And again, 14.5 is kind of a standard for most gears. Most gears are either 14.5 or 20, I believe. FRC is 14.5. Face width 0.5. I think you can change this. Yep. So you make the gear thicker if you want to. And then shaft, you can kind of do whatever you want. And yeah, and so if you want to put a hex shaft in a gear like this, oh, I put a keyway. What the heck? I don't want that. None. There we go. So if you want to put like a hex shaft in this gear, what you would do is make a smaller circle shaft, so like a quarter or something is probably okay. Hit check, which will kind of form the gear. Oh, where did it go? There it is. Hold on, let me make this thing full screen. You can go and then create a new sketch. So sketch on this front plane. Make sure that we're now in our correct units, which I believe, okay, there we go. We are. Hit polygon. Dimension face to face to be 0.5 inches. Features, extrude cut, and through all. And now we have a hex bore in our gear. Okay, so now I'm going to talk about how to make kind of more abstract shapes like this polycord that I made last year for 2020's robot. It's kind of like a circular shape, and it's what they call a sweep cut. Sweep boss, kind of sweep boss extrude. And what you pretty much do is, I'll show you guys, you pretty much create a shape that you want to extrude along a path. So I created a circle, and I extruded it along this whole circular path here. And so it's important to note that SolidWorks isn't very good at making kind of abstract shapes. There are features such as this that you can work your way around and kind of do roughly what you want. But there are much better software such as Maya or more sculptural softwares, 3D CAD softwares that are better for doing kind of more abstract sculptural shapes. But because we use SolidWorks, there are some features that we can utilize to do similar things. So let me open my part. So to use this sweep boss feature, first thing you want to do is create a sketch, which I just did. Then you're going to want to create some path first that you want your shape to go around. So this is kind of random, but you get the idea. Then you want to X out of that sketch. You want to go over here and select a plane that's perpendicular to the sketch you've just drawn, right? So we drew it on this front plane, and the top plane is perpendicular to that plane. So we're going to go ahead, click top plane over here in the idea tree, right click, hit sketch, and we can then go in and draw whatever shape we want to. So we're going to draw a circle, dimension it with a diameter of 1 is probably okay, or sorry, 0.1, and then exit the sketch as well. So now you can kind of see we have the shape we're going to be extruding along the path that we're going to be extruding. So you can go over to features, hit this sweep boss base feature, and so you can see kind of blue box what we're currently working on, and this blue box is asking for the shape you're trying to extrude. You can kind of see it's highlighted in blue over here on this icon. So for us, that's our circle. You can select the circle, and this one is kind of showing you we're trying to select the path that we're going to be extruding this circle along, which is this kind of boxy shape. And as you can see, it kind of previews what we want it to preview. You can hit check, and now we have the shape extruded along this kind of non-conventional looking path. Okay, so now I'm going to go over some of the less commonly used features of a sketch that SolidWorks offers, but they're still important to know, and I'm going to go over them kind of quickly. So one of the features I sometimes use, but not very often, is the mirror feature. And so to demonstrate that, I'm first going to kind of also show you a new feature, which is this spline curve. If you click on it, you can kind of see it tends to draw like curvy lines. And so what you do is you click on it, you choose your start point, and then, so for example, say you want a curve, and you want the middle part of the curve to be like 5 inches from the flat part like this. You'd hit this, hit your point, and then go over, hit it again, and then hit escape, and it creates a curve. And then for the mirror features, mirror entities, say I want to create like I don't know what you want. I don't know. I use it for like some sort of symmetrical intake game manipulator piece. But if you hit mirror entities, it asks you what entities you want to mirror. So I want to mirror this line. I want to mirror it about, and that is pretty much asking what line you're going to mirror those entities across. So I'm going to mirror it across this line. You can see it previews the shape, and now we have kind of a symmetrical piece like this. That's kind of a good feature to know. Another one I actually use quite a bit is the revolve feature. I'm not sure. Yeah, so here it is. It's revolved. I've keyboard shortcut it to R, which is pretty helpful. So first it asks for axis of revolution, which will be like this center axis right here, whatever axis you want to revolve your shape around. Then it asks for the contours you want to revolve. So I'm going to revolve these two. And now you can kind of see it revolves at 360 degrees into this weird looking acorn shape, or whatever shape you want it to be. Okay, so lastly I want to show you guys how to make a countersink hole for a screw. And I do this a lot when I'm doing 3D printed things, or even CNC things, honestly, you can do it too. But if you want to countersink a bolt into the 3D printed part to kind of get a lower profile, or, you know, kind of whatever you need, you could do that. And so I did this when I did the 2020 robot turret black plastic ring, I wanted to countersink some of the bolts into the plastic to kind of make it a more smooth, lower profile ring. And how you do that is I have a box here just for an example. You're in features, you can select this whole wizard feature. And you can see this is all different types of countersinks you can do. So there's hex countersinks, there's circular ones, all sorts of stuff. I'm just going to do the kind of traditional angled one right here. And this is where you can select the size of your bolts, how big the head is, the degree. 85 is pretty standard. And so if we're doing, we use a lot of 0.2 inch bolts. So 0.2 and 0.35 are settings I have left over from kind of those bolt dimensions. So that's all set. You can also select like how deep you want it to be. So if you have like a 2 centimeter long bolt or like a 1.2 centimeter long bolt, you can do that. And then you're going to go over here once all these settings are all set, go into position, select the sketch, and then you can go in and place it wherever you want it to be. And now we have a kind of like countersink hole for the bolt. And to wrap it all up, a couple things I want to say to you guys. First of all, if you're ever having difficulties, like, you can honestly just Google about anything, search on YouTube, all that kind of stuff. I learned about 95% of all the CAD I know now from YouTube, from watching videos, Googling things. Issues are going to come up. You're going to have errors. Things are going to get deleted. You're not going to know how to do something. And if you just Google it, search it on YouTube, I'm sure you can find it. This is a very widely used platform, SolidWorks is. People have been doing this stuff for a long time. It's been around for a long time. And the other thing is, don't expect to have amazing results right off the bat. Like, this is 2020's robot, and there are over 1,000 components in this. Like, this took hundreds of hours, and while yes, it was extremely helpful to have kind of a full robot CAD to understand how things are going to get laid out, and I think it was a huge part of our 2020 success. If you're, if this is your first year doing CAD, your first week doing CAD, you're not going to have results that are going to be like hundreds of hours of time into fully built robots, right? And you can kind of divide up tasks, put one person on intake, one person on shooter, all that kind of stuff. But still, it just takes time. It takes time to learn this kind of stuff. I've been doing CAD for 3 years now. And so just don't be disappointed or upset if you can't get something done and it's frustrating you. Just walk away and come back and try it later. Okay?